Hello friends, I hope everyone is doing great. Today I would like to take you to episode 3 or part 3 of the solved past paper questions under electricity and DC circuits. These are multiple choice questions, physics 9702. Do not forget to download the documents which have these multiple choice questions. The video description has the links to the documents. It has the links to paper 4, links to paper 2, and links to multiple choice questions or the link to multiple choice questions for paper 1. So do not hesitate to download them. They are completely free. Completely free. Everything is free of charge. So learning is free. So without wasting time, I would like to take you to part 3 of these videos. So I think in part 2, we must have stopped on this question here. That is on page 41. So we stopped on page 41 and I want us to start from the same page. Okay, so we're here. In the circuits shown, the power supply has an e.m.f. greater than the normal operating voltage of the lamp. The e.m.f. is greater than the normal operating voltage of the lamp. The internal resistance of the power supply is negligible. The resistance of the variable resistor is adjusted from 0 to maximum value. So the resistance is adjusted from 0 to maximum value. In which circuit could the voltage across the lamp change from 0 to the normal operating voltage and not exceed its normal operating voltage? Okay, so we can try to inspect these. These circuits which have been given. In the first case here, because we have a fixed resistor across the lamp, it means the PD across the fixed resistor is always going to be equal to the PD across the lamp. And therefore it means the PD across the lamp will never go below 0 because the resistance of this can never be 0. So it means A is not going to be correct. We want the PD across the lamp to change from 0 to its normal operating voltage. So here it will never be 0 because the fixed resistor has some resistance, so its PD can never be 0 if there is a current flowing. Then here we can also try to inspect this. Here it is showing that the variable resistor is in series with the battery. It means as there is a current flowing through the lamp, it means the PD across the lamp will never be 0, so this one is also out. Then we go to this one, we go to inspect B. So in B, there's a fixed resistor here. That means there will always be PD across the fixed resistor. And the variable resistor is across the lamp. And when the variable resistor has resistance 0, it means the PD across it is 0, so the PD across the lamp will be 0. And when the variable resistor has a certain resistance or has its maximum resistance, then the PD across the lamp will be equal the same as the PD across that. That means the answer is most likely going to be C. So you may be wondering, why not D? In D, there is no any other resistor connected with the power supply, meaning that the PD across the lamp can exceed the normal operating voltage, yet it should not exceed the normal operating voltage. Therefore, our answer is going to be B. Three identical lamps, L1, L2, and L3 are connected to a battery with a negligible internal resistance as shown here. Okay. So what happens to the brightness of lamp L1, L2 when the switch S is closed? So initially, when S is open, L1 and L2 are in series. When S is open, they are in series. So it means the e.m.f. here is going to be divided across these lamps. So they have certain brightness. When this is closed, when S is closed, it means total resistance here. The total resistance here is going to decrease. The resistance here decreases because these are in parallel. This reduces the resistance. So total resistance through the circuit is going to decrease. In fact, the resistance across the parallel combination is going to be smaller, which means the total resistance is actually smaller. But remember, the PD across L2 is the same as the PD across L3. Since the total resistance is smaller, it means the PD across L2 and 3 is also going to be smaller. What does that mean? L2 therefore be dimmer than it was before because the PD across it is now less. So let's check. L2 is going to be dimmer. So L2 must be dimmer. So we have this one option and this option here. So this is wrong. Then if L2 is dimmer, let's check L1. Note that total resistance has decreased. That means total current in the circuit has actually increased. Total current in the circuit has increased, but remember the resistance of L1 has not changed. And since total current has increased and V is equal to I times R, total current has increased because all the current through the battery goes through L1. It means the PD across L1 is going to be actually greater, which implies that L1 is going to be brighter. Therefore, our answer is going to be brighter and dimmer, so the answer is going to be B. In the circuit shown, the 6-volt battery has negative internal resistance. Resistors R1 and R2 and a voltmeter each have a resistance of 100 kilo ohms. What is the current? What is the current in the resistor R2? So first of all, we can find the total current. The question is, what is the current in the resistor R2? So we can first find the total current. To find the total current, we need the e.m.f divided by total resistance. Remember, these two are in parallel, so the combination will give us 50 kilo ohms. You might always be wondering, why do I just get the one resistor divided by 2 whenever they're in parallel? Remember, resistance in parallel, if there are two, 1 over total is equal to 1 over the other resistor, which is 100, plus the other one, which is also 100. And they are identical. So this is the same as 2 over 100. Then we get the reciprocal. So R total is going to be 100 over 2. That's why whenever I have identical resistors, I just take half of the resistance of one as the effective resistance. So here we have 50 plus 50 is now in series with 100. That gives us 150 kilo ohms. So this is going to be e.m.f, which is 6 divided by 150 times 10 power 3. So that is the total current which is entering this junction, but because they are identical, it divides equally. So I'm going to divide this by 2 to find the current through R2. So I through R2 is going to be 6 divided by 2 times 150 times 10 power 3. This 2 here, I'm dividing the total current I by 2. It is divided equally at the junction because the resistors are identical. So from my calculator, I have 6 divided by 2 times 150 exponent 3. So that gives us 2 times 10 power 5, negative 5 amperes. The answers have been given in milliamperes, so I will say 2 times 10 power negative 5 divided by 10 power negative 6 to change it to microamperes. So divide by 1 exponent negative 6. That is 20. So the current there is 20 microamperes. So our answer is A. In the circuit shown, a fixed resistor X is connected in series with a battery and a variable resistor. The power dissipated in resistor X is 7.2 watts when a current of 3.0 amperes passes through it. Let's first find resistor X. So we know that power is equal to I squared times R. So the power is 7.2. The current is 3.0 squared times R, which means R is going to be equal to 7.2 divided by 9 ohms. I may not need to divide that now. Then the variable resistor is adjusted so that the power dissipated in X increases by 50%. So the variable resistor is adjusted so that the power dissipated in X increases by 50%. So the new power we'll call it power 2 is going to be 7.2 plus 50% of 7.2. 50%, that is 50 over 100 of 7.2. 50% is a half, so that means this is going to give us 7.2 plus, the new power here is 7.2 plus 50% of 7.2 is 3.6. So the new power is going to be 10.8 watts. I think that is 10.8 watts. Okay, so that is the new power. What is the new current in the circuit? So let's find the new current in the circuit. So current is going to be equal to, of course, we know we are using the same formula, power is equal to I squared R. So the current is going to be equal to the square root of the power divided by the resistance R. We have already seen the resistance of X because the resistance of X is fixed. This was the resistance of X. So this is going to be the square root of the power. The new power is 10.8 divided by the resistance of X, which is I think 7.2 is divisible by 9. 7.2 divided by 9, that is 0.8. So this is 0.8 ohms. So we're dividing the power by 0.8 ohms. That is the resistance of X, which is fixed. And this gives us 10.8 divided by 0.8. Then we find the square root of the answer. That is 3.67 or approximately 3.7. So this is going to be 3.7 amperes. So our answer is going to be B. A resistor and a filament lamp are connected in series with a power supply. The IV characteristics of the resistor and of the lamp are shown below. So for resistor, it is obviously supposed to be a straight line because V is directly proportional to I if the temperature does not change. A filament lamp, it can't be a straight line because as V increases, there comes a point when the lamp filament overheats. And if the lamp filament overheats, it means the temperature has increased, and temperature is directly proportional to resistance. So if the temperature increases, the resistance increases. That's why you see the graph tends to becoming horizontal. The potential difference across the resistor is 3.3 volts. So let's look for 3.3 here. On the x-axis, the scale is 1 divided by 5, which is 0.2. So one box here is 3.2. Then half a box is 3.3. I think 3.3 is going to be here in this box here. So 3.3 is there, which gives us 0.3 as the current. So because they are connected in series, the current in the lamp is the same as the current in the fixed resistor. What we are having here as a circuit is like this. We have a fixed resistor and we have a lamp. These are connected in series with a power supply, or with with a power supply. So it means the current through the lamp is the same as the current through the fixed resistor. And if the PD across the fixed resistor is 3.3 volts, which has given us a current through the circuit as 0.3. So the same current must be flowing through the lamp. So let's look for 0.3 current. So a current of 0.3 gives us a voltage, a PD across the lamp of 4.2. So this is 4.2 volts. So the question is, what is the resistance of the lamp? So to find the resistance of the lamp, we can, because the PD across the lamp is 4.2 and the PD across this one is 3.3, we may just find the EMF. So the EMF is going to be the PD across the lamp, which is 4.2, plus the PD across the fixed resistor, which is 3.3, giving us a total of 7.5 volts. that is the EMF. And to find total resistance, we know that total resistance is equal to EMF over total resistance is equal to EMF over the current, or current is EMF over total resistance. So total resistance is going to be 7.5 divided by the current, which is 0.3. So we can check this. 7.5 divided by 0.3, that is 25. So this is 25 ohms. That is total resistance. And what is the resistance of the fixed resistor? We can also find that one. Resistance of the fixed resistor, resistance of the fixed resistor here, resistance of fixed resistor, this side is going to be the PD, which is 3.3, divided by the current, which is 0.3, and I think that is 11 ohms. So the resistance here is 11 ohms. All we want is the resistance here, but total resistance is 25 ohms. So what does that mean? The resistance of the lamp is going to be equal to 25 minus 11 because they're in series. So 25 minus 11, I think this gives us 14, making our answer to be D. Okay. A car battery has EMF 12 volts and an internal resistance 0.05 volts. The battery is connected to the starter motor of a car. The current in the motor is 160 amperes. What is the terminal PD across the battery? So we know that EMF is equal to current is equal to the terminal PD. I'll use V capital T for terminal PD plus the lost volts. So that is EMF. So we want terminal PD across the battery, PD across the battery terminals. Note that the lost volts is given by current times resistance. Okay, so the terminal PD, VT, is going to be equal to EMF minus the lost volts, which is current, times small resistance. So this is going to give us the EMF is 12 minus the current is 160 times the small resistance, internal resistance, which is 0.05. So this is going to give us 12 minus, open brackets, 160 times 0.05, which gives us our answer as 4 volts. So the terminal PD is going to be 4 volts, and that is B. A cell of negligible internal resistance is connected to a network of resistors and a voltmeter as shown. You notice that this is a Wheatstone bridge. It is a Wheatstone bridge. I think that is the spelling of bridge, Wheatstone bridge. And remember what I said, if you have a Wheatstone bridge, Wheatstone, is it Wheatstone? It is Wheatstone. I think it is Wheatstone bridge, whatever it is. So remember I said when you have a Wheatstone bridge, in the laboratory when you connect it, you will realize that the product of these adjacent resistors will be the same as the product of these adjacent resistors, and we call this the crisscross approach. So we shall check this. Remember these are in parallel. So total resistance here is going to be R times 14.4 over R plus 14.4, the total resistance here. So the product should be the same using the crisscross method. So let's start from here. We have 3.00 times 4.8 should be equal to 2 times the other one, which is R times 14.4 over R plus 14.4. So just solve that. We are just going to solve that equation. So what is 3 times 4.4? 3 times 4.8, that is 14.4. I'll just divide this by 2, 7.2. So we have 7.2 is equal to 14.4 R over R plus 14.4. So you just collect like terms. So you have 7.2 R plus 14.4 times 7.2 plus 103.68 is equal to 14.4 times r. So I bring this one the other side, it will be 7.2. So it means r is going to be 10.3.68 divided by 7.2. And surprisingly, I'm getting the answer as 14.4. So r is going to be 14.4. So this answer is going to be D, 14.4. A voltmeter is connected into a circuit with polarity shown in the diagram. The sliding contact is moved to end P. The sliding contact is moved to end P of the potentiometer. That means if the sliding contact is moved to point P, there will be no potential difference. Voltmeter will be 0, so C and D have been cancelled out. Sliding contact and then to Q. So if it is taken to Q, if this is taken to Q, it means the voltmeter, it will be equivalent to having something like this. We shall have the voltage supply, which is 3 ohms, and we have our resistor here of, then the contact is here, so this one is here like this, and then the voltmeter is here. The voltmeter is somewhere here. Remember, this is positive, then this is negative, and this is going to be 3 volts. Let me reduce this. So here we have 3 volts, and here we have 3 volts. So what will be the reading of this voltmeter here? In other words, simply find the reading of that voltmeter. It is supposed to give us the PD, the potential difference. So I can draw a loop. I'll draw a loop in here. Let me make the loop to be clockwise. It means I've left out this part here. So the reading of the voltmeter, I've left out this branch here. So the reading of the voltmeter would be sum of EMFs will be equal to the PD. So sum of EMFs is 3 volts plus 3 volts because they are in the same, this is positive, negative, and I'm moving around the loop clockwise. So it is 3 volts plus 3 volts, which is equal to 6 volts. Therefore, my answer is going to be B. So the reading of the voltmeter will be the sum of the EMFs because the resistor, which is here, has been left out when I draw that loop. So the answer is going to be B. Two resistors R1 and R2 are made from wire of the same material. They are connected in parallel to each other in a circuit as shown here. The diameter of R2 is half the diameter of R1. The resistance of R2 is 3 times the resistance of R1. What is the ratio? The value of the ratio of average drift speed of R1 over average drift speed of R2. So first of all, we notice that current through the given circuit, or the PD, is going to be equal to I1 or I times R. That is the PD. And the PD is the same because they're in parallel. We also notice that the current I is equal to NEVQ. No, NEVA, because I've used the E for Q. So the current, the PD across R1 is the same. So I will say PD across R1 is the same as PD across R2, which means that I1 R1 is the same as I2 R2. So this implies that I1 divided by I2 is going to be the same as R2 divided by R1. But remember, R2 is 3 times R1, so this is 3 times R1 over R1, which gives us 3. So precisely we are seeing that I1 divided by I2 is equal to 3, because R1 here cancels out. I1 over I2 is equal to 3. In other words, I1 is 3 times I2. Okay. And now we go and employ this expression here. So I'm just going to say I1, remember, is going to be N times E times V1. And the area for area, remember, area is equal to pi d squared over 4, or pi r squared. So for 1, the diameter of R2 is half the diameter of R1. If R1 is d, so this will be pi d squared over 4 for R1. Then for R2 it will be NE, the drift speed will be V2, the area will be pi. Where there is diameter, the diameter of R2 is half. So this is going to be a half of d but squared divided by 4. This should be giving us 3. I'll change the color to cross out some of these things. NE has cancelled, pi has cancelled, the 4 in the denominator has cancelled. So I remain with V1 over V2. In the numerator I also have d squared. In the denominator I have a half d squared, which is a quarter. A quarter d squared should be equal to 3. So d squared has also cancelled out. This squared has also cancelled out. So I now multiply both sides by a quarter. So it means V1 over V2 is equal to 3 times a quarter. So this gives us 3 over 4. Therefore, now I know people will just multiply the other side by 4. But it's 1 over 4. So we multiply the other side by 1 over 4, this side by 1 over 4, the other side by 1 over 4. That's how it cancels here. So it becomes 3 over 4. So our answer is going to be B. A student describes potential difference as the energy transferred per unit charge. Which statement about the energy transfer is correct? PD is the energy transferred from electrical to thermal per unit charge. So it only takes place, it is a form of electrical energy into other forms. That is alternative number 1. It is a form of electrical energy into other forms. I said PD is electrical to thermal, alright, so I think that is the most appropriate alternative. If it was EMF, it would be chemical to electrical. This one is electrical to other forms, so the answer is A. A metal cube has a resistance of 4 ohms between opposite faces. 10 of these cubes are put together to make a cube weight 1, so the other side is 1 by 2 by 5. So it means there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 2 in parallel, there are 5 in series, and another 5 in series. Then the combination of 5 is in parallel. So let's say Y is here and X is here. These 2 are in parallel, these 5 are in series with each other, these 5 are in series with each other, and then the combination is in parallel. So you have 4 plus 4 plus 4 plus 4 plus 4. So here up we have 20. 4 times 5, that is 20 ohms there in series. And here we have also 20 ohms in series. But the 20 ohms in series and the 20 ohms in series are again going to be in parallel if uh, if we put a connection across X and Y. Therefore, again we find resistance in parallel. So we now going to have 1 over total resistance in parallel is going to be 1 over 20 plus 1 over 20, which is equal to 2 over 20, which implies that we get the reciprocal. So total resistance in parallel is going to be 20 divided by 2, which is going to be 10 ohms. Notice each had 4. That's why I have 4 plus 4 plus 4 plus 4 plus 4. These are in series, giving me 20. The lower ones are also in series, giving me 20, but then the connections are put across here, meaning the 20 and the 20 are in parallel. which gives us a total of 10. So our answer is going to be C. A cell is connected to a fixed resistor. Over a long period of time, the internal resistance of the cell increases. What is the effect of the increase in internal resistance on the e.m.f of the cell and on the power dissipated by the fixed resistor? So a cell is connected to a fixed resistor. So let's see what is happening here. So a cell is connected to a fixed resistor. Over a long period of time, the internal resistance of the cell increases. So it means the cell has an internal resistance. So let's have a small resistance somewhere here. Okay. Let this be the cell and the small internal resistance. And then we have a fixed resistor somewhere here. So it's like the internal resistance of the the internal resistance varies. So that is small r, this is capital R. What is the effect of the increase in internal resistance on the e.m.f of the cell and on the power dissipated by the fixed resistor? Of course, the e.m.f does not change even if the internal resistance increases. The e.m.f is the total energy available, so it cannot change. All that is affected is the terminal PD. And if the terminal PD is the one which is affected, then the power dissipated or the power given out to the fixed resistor will be affected. Okay, so if internal resistance increases, it means total current in the circuit, I total, is going to be decreasing. And the power dissipated in the fixed resistor is that current squared times R. R is fixed. Because the current is reducing and R is fixed, it means the power is reducing. Therefore, there will be no change to the e.m.f, but the power dissipated decreases because the current decreases when R increases. Small r increases. 4 identical resistors are connected in a circuit as shown. They are identical. Let's say each has resistance R. So these two are in series. They give us total resistance 2R. These ones are in parallel. So we have 1 over R plus 1 over R, which is 2 over R. We get the reciprocal. So that is R over 2. So total resistance here is R over 2. So let's see the question. The battery has negligible internal resistance and an e.m.f of 30 volts. What is the potential difference between two points X, the 2 points X and Y? So we want the PD across X and Y. Okay, we have to find the total current. So current is equal to e.m.f divided by total resistance. Total resistance will be 2R plus R over 2. So the e.m.f is 30 divided by 2R plus R over 2. 2R plus R over 2, I think it is 5R over 2. So the current is going to be 30 divided by 5R over 2, which is going to be 60 over 5R over 2, which is actually 12 over R. That is 12 over R, amperes. That is the current. So to find the PD across X and Y, PD from Ohm's law V is equal to IR. The current is 12 divided by R, and the resistance across XY, so this will be RXY. Resistance across XY is twice R, which makes this to be 24. So our answer is going to be precisely D. A power supply and a solar cell are compared using the potentiometer circuit shown in the figure. Remember, potentiometer compares e.m.fs or PDs. The potentiometer wire PQ is 100 centimeters long and has a resistance of 5 ohms. So PQ is 100 centimeters and has a resistance of 5 ohms. The power supply has an e.m.f of 2 volts and the solar cell has an e.m.f of 5 millivolts. Which resistance R must be used so that the galvanometer reads 0 when PS is 40 centimeters? So we want the galvanometer to read 0 when the PS is 40 centimeters. So let's first find the resistance across PS. I don't think the resistance is necessary. Let's just find the current through PS. So to find the current through PS, we shall first of all find the PD across PS. When the galvanometer reads 0, it means the PD across PS is the same as the EMF of the solar cell. So the PD across PS is going to be the same as the EMF of the solar cell, which is 5 millivolts. So I'll say 5 times 10 power negative 3 volts. That is the PD across PS. And the resistance of PS can also be found because we have the resistance for the whole wire and we have the length. Resistance is directly proportional to length. So resistance across PS is going to be 40 over total length, which is 100 centimeters, times the resistance of the whole wire, which is 5. So 5 over 100 is resistance per centimeter. So when I multiply by 40, I get resistance of only PS. So this is, I think, 200 over 100, that is 2 ohms. So the PD across PS is 5 volts because when there is balance, the PD across PS is the same as EMF of the solar cell. So if I want the current, find the current through PS, this is going to be V over R, which is going to be 5 times 10 power negative 3 divided by 2, which gives me 2.5 times 10 power negative 3 amperes. So that is the current through PS. Okay. So which resistance R must be used so that the galvanometer reads 0 when PS is equal to 40 centimeters? So let's find also SQ. Let's find the PD across SQ. So the PD across SQ, PD across SQ is going to be current through SQ times resistance of SQ. If resistance of PS is 2 ohms, it means this is 2 ohms. It means the other one is 3 ohms. And remember, note that they are in series. If there's no current flowing through the galvanometer, then the current through PS is the same as the current through SQ. So this is going to be equal to 2.5 times 10 power negative 3 times 3, which gives us 2.5 times 3, I think that is 7.5. So this is 7.5 times 10 power negative 3 volts. That is the PD across SQ. Now we can find the PD across R. Note that the total EMF is 2. So I know the PD across PS. I know the PD across PS. I know the PD across SQ as 7.5 volts. So I should now be able to find the PD across R. So the PD across R is going to be equal to the PD across PQ, which is going to be, so it is going to be 2 minus the PD across PQ, which is going to be the sum of these two, this one plus that one. So I have 7.5 plus 5, which is 12 point, is it 12.5? 2.5 times 2.5 exponent negative 3 times 3 is 7.5. Okay. So this is going to be R, okay? So that is 0.0, the other one is 5 millivolts. Okay, so the potentiometer wire is 100 centimeters long and has a resistance 5 ohms. The power supply has an EMF of 2 volts, and the solar cell has an EMF of 5 millivolts. Okay, so it means the PD across R is going to be 2 minus 0. This is going to be 0.0175. Is it 175? Plus 5 exponent negative 3. No, it is 0.0125. 0.0125. Okay. So if I add the PD across this plus this PD, that is 0.0125. Let me try to erase this because it is confusing here. Okay, so I'm saying 2 minus the PD across PQ, which is 7.5 times 10 power negative 3 plus 5 times 10 power negative 3. Okay, so this is 2 minus 0.0125. So 2 minus the answer there, sorry, 2 minus 0.0125, that gives us 1.9875 volts. Okay, let's now find the resistance. It is a long process, but resistance is going to be the P, which is 1.9875. Of course, the current will be the same, which is 2.5 times 10 power negative 3. So I'll say the answer divided by 2.5 exponent negative 3, which is 795. So R is 795 ohms, making the answer to be C. Okay. So notice I first found the PD across PS. I was able to find the PD across SQ, then I combined them. When I combined them, I subtract them from 2 to find the balance, which is the PD across R. After finding the PD across R, since there is no resultant current through the galvanometer, so the same current was flowing in that circuit, which is 2.5 times 10 power negative 3. So I use that current, and this gives me the resistance at 795. The electric current in a wire may be calculated using that equation. Which statement is not correct? Not correct. N is the number of charge carriers per unit volume. I think that is correct. NA is the number of charge carriers per unit length. So we know that volume is cross-sectional area times length. And N is the number of charge carriers over volume. So it means, remember, volume is A times L. So a number of charge carriers per unit volume, that is N. So it means if I multiply both sides by A, so this side by A, the other side also by A, I have NA that side. This side I have number of charge carriers, area over volume is L. So I have volume, area over volume, that is then times number of charge carriers. So Na is the number of charge carriers per unit length. Remember, A over volume is L, so this is Na equals to L times the number of charge carriers. So number of charge carriers is Na over L, so this is also correct. Q is the charge of each charge carrier. I think this is also correct. V is the velocity. Why did I waste time? V is not the velocity. It is actually the drift velocity, the average drift velocity. So this one, D, is not correct. It is not just velocity. It is the average drift velocity. Three resistors are connected in parallel across a power supply. So they're in parallel. The power dissipated in each of the resistors is of resistances 2 ohms, 3 ohms, 4 ohms, P2, P3, P4. What is the ratio P2 to P3 to P4? So we know that power is equal to V squared over R. V is the same. So the power here, which has been called P2, P2 is going to be V squared over 2, P3 is going to be V squared over 3, and P4 is going to be V squared over 4. So let's find the ratios. The ratios are going to be V2 squared over 2, V2 squared over 3, V squared over 4. So that is the ratio of the powers. So ignoring V and getting the LCM here, the LCM is equal to, I think the LCM is 12. The LCM here is 12. So I'm going to multiply everything by 12 over V squared. So everything by 12 over V squared. So I'm multiplying this times 12 over V squared. So this becomes by 12 over V squared, so that will be 6. By 12 over V squared, that will be 4. By 12 over V squared, this will be 3, making our answer to be C. So I multiplied by 12 over V squared. 12 is the LCM of all these ones. Which graph shows the variation with the current I of the potential difference of a filament lamp? At this point now we know the IV characteristic of a filament lamp. So this is wrong, that is wrong, that is wrong. The answer is going to be D. Is that? Oh, it is V against I, so it is the other way around. If it was I against V, it would be D. It is V against I, so it is A. Because I is on the x-axis, the point reaches where the change in current becomes smaller because the resistance increases as temperature increases for a filament lamp. So this change in current occurs when the resistance increases. A wire of cross-sectional area, or by the way, you can even look at it in terms of R is equal to V over I. R is equal to V over I, or V is equal to R times I. Note that R is going to be the gradient. R is the gradient. So as V increases, when temperatures increase, the current is also increasing. But when temperatures increase, the current is going to decrease. And if the current decreases, when V is increasing, it means the resistance must be increasing, which means the gradient increases. So the gradient is going to be increasing because the change in I is going to be decreasing. A wire of cross-sectional area 5 times 10 power negative 6 is made of a metal of resistivity 50 times 10 power negative 8 ohm meters. The potential difference across the wire is 6 volts. So PD across the wire is 6 volts. And the current is 3 amperes. What is the length of the wire? What is the length of the wire? So that is very easy. So we know resistance is equal to rho L over cross-sectional area. And we also know, so they have given us the cross-sectional area straight away, they have given us the resistivity, and we don't have the resistance, but they have given us V and I. We also know that R is equal to V over I. So it means the length L is going to be resistance, which is V over I, times the cross-sectional area, divided by rho. In other words, L is going to be V, which is 6, times area, which is 5.0 times 10 power negative 6, divided by I, which is 3.0, resistivity, which is 50 times 10 power negative 8. 6 times 5 exponent negative 6, divided by 3 times 5, 0, exponent negative 8. So I am getting the answer here as 20. So the answer is going to be D. So this is giving us 20 meters, which means the answer here is going to be D. A metal wire, a cell of internal resistance R and e.m.f. E is connected in series with a resistor of resistance R, as shown here. The resistance R and e.m.f. E remain fixed. The internal resistance R of the cell changes over time. Which graph best shows the variation of the current I in the circuit with the internal resistance R? Remember, we have already seen that e.m.f. is going to be I into R plus small r. If I make I the subject, I is going to be the e.m.f., which is fixed, remember, over the fixed resistor, capital R. It is only small r which is changing, so these ones I'm putting in curly brackets are fixed. It is only small r which is changing, and it is being increased. The internal resistance R of the cell changes over time. Let's say it increases because the graphs are showing it is increasing. So if internal resistance increases, of course it means the denominator is going to be bigger, the current must decrease. If we see in a graph where the current is constant or increasing, then that is wrong. So this one is wrong, because this one is showing the current is remaining constant. But then this variation here cannot be linear. Yes, the current is decreasing, but this variation cannot be linear. And when R is 0, the current I is not 0, because there is a value of E over R. So it means the graph should not be touching the y-axis at R equals to 0. So that means this is automatically wrong. And this is, when R is 0. Okay, when R is 0, I has a current. So the graph must touch the y-axis, which means this is wrong. We remain with the two options. When R is 0, I is not 0. I starts from a certain value on the y-axis. So it means there's a value. The graph must touch the y-axis. When R is 0, small r is 0, I is a certain value, which means I should be a value on the x-axis, on the y-axis when R is 0. So, but this one is showing I is almost infinity as R tends to 0. So we remain with the two options C and B. But I say this cannot be a linear relationship. Therefore, our answer is going to be B. It cannot be a linear relationship, so our answer is going to be B. Identical resistors are connected in 4 combinations P, Q, R, and S between terminals X and Y. What is the order of decreasing combined resistance between X and Y? Largest first. So which one is the largest? I think the largest is going to be P. If I'm not mistaken, this is going to be 2R. This is R. And this is going to be a half R because they're in parallel. So this one is a half R plus R. This is a half R plus R, which is going to be 3 over 2 R. 1.5 R. So the largest is P. So this C and D are wrong. Then the smallest is going to be, this is R, 0.5 R, 1. The smallest is going to be R. So this is wrong. Our smallest is this, because this is 0.5 R, this is 1.5 R. So the smallest is R, is this one here. So our answer is going to be A, because P is the largest and R is the smallest. So our answer is going to be A. The circuit shown consists of two resistors of resistance 10 kilo ohms and 50 kilo ohms, and a component Y. A 6-volt supply is provided. The electric potential of the bottom wire is 0 volts. The current in component Y is negligible. What is the electric potential at junction X? Electric potential at junction X. That is very simple. We shall use potential dividers. V out is equal to R over R total times V in. So PD across X and the 0 volt is going to be the resistance, which is 50. Total resistance there is 50 plus 10, which is 60. The kilo ohms, of course, cancels out. Then times V in, which is 6 volts, and that is 50 divided by 60 times 6, which is 5. So this is 5 volts. The answer is D. In an electrolyte, the electric current is carried by charged particles in a solution. What is not possible? Not possible. What is not a possible value for the charge on an ion in a solution? So we know that charge is going to be equal to the number of electrons times E, where N must be a whole number. Charge is a multiple of the elementary charge. So I'm saying N must be a whole number. N must be a whole number. So N is going to be charge given divided by E. So we are just going to check. We are going to check by simply dividing. So I'll check 4.8. They said which one is not possible. So we have 4.8 exponent negative 19 divided by 1.6 exponent negative 19. That's a whole number, so that is possible. Let's check the second one. The second one is 1.6, that is already possible. The third one is 3.2 divided by 1.6. It is a whole number, that is possible. The fourth one, 4 divided by 1.6. That is not a whole number, so this one is not possible because charge must be a whole number times 1.6 times 10 power negative 19. In other words, you have seen that when I get 4 times 10 power negative 19 equals to N times 1.6 times 10 power negative 19, N is 2.5, which is not a whole number, so that is not possible. Charge is quantized. A potentiometer connected between 2 points P and Q in an electrical circuit shows a reading of 1 volt. So it shows which statement is correct. So it is showing a reading of 1 volt. Current flows from positive to negative. So current must be flowing this direction. If current flows from positive to negative, then electrons flow from negative to positive. So the electrons are in that direction. So which statement is correct? The energy needed to move positive 1 coulomb of charge from P to Q is 1 joule. The energy needed to move positive 1 coulomb of charge from P to Q is 1 volt. The energy needed to move positive 1 coulomb of charge from Q to P is 1 joule. So the answer is going to be B, because the work is going to be done against the repulsion if a positive charge column is moved from Q to P, where P is positive. So the work done against this repulsion is the energy transferred, or the energy needed is the work done against this repulsion. Therefore, the answer is going to be B. So there is no work done, there is no energy needed to move from P to Q, because a positively charged particle would naturally move from P to Q, because P is at high potential and Q is at low potential. But moving from Q to P, a positively charged particle needs energy. Therefore, the answer is going to be B. Which graph best represents the variation of I of potential difference V for a filament lamp? Of course, for a filament lamp, remember, as PD increases, the current increases, but there is a point where even though PD increases, the change in current becomes smaller. That is, the resistance increases because the temperature of the filament increases. Therefore, our answer is going to be B. You can think about it in this way: V is equal to I times R, and if it means the gradient which is equal to R is going to be V over I. So for a filament lamp, the resistance increases when temperatures increase, which means the gradient must be increasing. So this means the gradient must be increasing. So this one is showing the decrease in gradient, a decrease in gradient. This one is showing an increase in gradient, and this one is showing an increase in gradient. However, for a filament, this one is showing the other side that the gradient decreases, yet it increases. So the answer is going to be B. When a battery is connected to a resistor, the battery gradually becomes warm. This causes the internal resistance of the battery to increase, whilst its electromotive force stays unchanged. As the internal resistance of the battery increases, how do the terminal potential difference and the output power change? Let's try to think about this by drawing a sketch. Let's draw a sketch. We have a battery with some internal resistance R. It is connected to a fixed resistor outside of resistance capital R. So this is our battery. Note that the EMF of a battery is equal to the terminal PD plus the lost volts. And it means that the terminal PD is going to be equal to the EMF E minus the lost volts. So when a battery is connected to a resistor, the battery gradually becomes warm. This causes the internal resistance of the battery to increase. Note that terminal PD is going to be EMF minus I times internal resistance. So the internal resistance increases, to mean the lost volts have increased. So the lost volts increase, which means the terminal PD decreases. So this one is going to be true. We have A and B now. What happens to the output power? What happens to the output power? The output power is going to be given by I times the terminal PD, but remember the terminal PD has already decreased. For the same current, because after all the internal resistance has increased, it means the current has decreased. Also, the terminal PD has decreased. It means the power also decreases. Therefore, our answer is going to be A. Terminal PD has decreased, the current has decreased, the power decreases. A cell is connected to a resistor of resistance 3 ohms. The current in the resistor is 1 ohm. A second identical resistor is added in parallel. The current becomes 1.93 amperes. What are the EMF and internal resistance R of the cell? Okay, so if we have a cell and a resistor, the current is that. We know that EMF is equal to current into R plus the internal resistance. So for the first case, the EMF was equal to the current, which is 1, the fixed resistor, which is 3, plus the internal resistance R. For the second case, the EMF, of course, doesn't change. is equal to the new current, which is 1.93. The fixed resistor is 3 plus the internal resistance R. No? A second identical resistor is added in parallel. Okay. Since the second resistor is added in parallel, then and the current is 1.9, then the new resistance is not 3 plus R. So we now have two resistors in parallel. Why can't I sketch this? The first case is like this. We have a battery which has internal resistance connected in series, connected with a fixed resistor R, which is of 3 ohms. So this is small r, that is E. For the second case, we have the same battery, the same internal resistance, and we have the same fixed resistor, which is connected in parallel with another fixed resistor. So this is 3 ohms, 3 ohms. So the total here is going to be 1.5 ohms because they're in parallel. We get 3 times 3 over 3 plus 3, which gives us 1.5 ohms. So the total resistance here is 1.5, then plus small r. So we shall say 1.5 plus small r. So what remains is to solve these two equations to find small r. How can I find? Okay, I'll just equate them because E is equal to that and E is equal to that. So I have 3 plus r equals to 1.93 times 1.5, which is 2.895, then plus 1.93r. So I'll collect like terms. I'll say 3 minus the answer, 0.105 is equal to 1.93 minus 1, which is 0.93r. So that answer divided by 0.93, that is 0.113. So it means small r is going to be 0.113. So it means this is wrong, this is wrong, this is wrong, which makes our answer to be C. Without even testing EMF, the answer is going to be C because small r is equal to that. A battery with a negligible internal resistance is connected to 3 resistors as shown in the figure there. All 3 resistors have the same resistance. So let's say it is R, R, R everywhere. These ones are going to give us a total of 2R. The other one will give us is R. So it means the current divides. If the current divides, it means this one will be is going to be because the resistance here is twice this one, the 3 amperes is going to be divided in the ratio of the resistances. So this one will take 1 ampere, 0.1 ampere, and the other one will take 0.2 amperes. Reason? The resistance this side is twice the resistance the other side. So the current the other side is going to be twice the current the other side. Okay. So the question is, what is the current in resistor X? That one is very simple. It is automatically 0.2. It's automatically 0.2 amperes because the current is inversely proportional to resistance. If the resistance here is twice the resistance there, then the current is going to be half the current there. So if I say that this is I and the other one is twice I, or this is twice I and this is twice I, if I say this is I, the other one should be twice I. So I can say I plus twice I is equal to 0.3. Still I is going to be 0.1. And since the current through R is twice I, so it is going to be 0.1 times 2, which is equal to 0.2. So the current here is 0.2 and this is 0.1. Note very carefully why I've chosen that arrangement. It is the ratio of the resistances. The current is divided in that ratio. The diagram shows a potentiometer and a fixed resistor connected across a 12 volts battery of negligible internal resistance. The fixed resistor and the potentiometer each have resistance 20 ohms. The circuit is designed to provide a variable output voltage. What is the range of output voltages? So if this goes to this point here, the reading automatically will be 0. So it means the minimum is 0. So this is out, this is out. When this is taken to this point here, then the PD, the V out, is going to be the ratio of the resistances is 20 over total resistance, which is 40 times 12. That is a half of 12, which is equal to 6 volts. So our answer is going to be A. A length of wire is connected into a circuit. The area of the cross section of the wire changes from A at R to a half A at S. There is a constant current in the wire. Charge Q passes R in a time t. What is the charge passing point S in the same time t? Okay, so we know that charge is equal to I times t. The current this side is the same as the current the other side. The current is the same. And if the current this side is the same and the current the other side is the same because they're in series, because the current this side is also going to be I times t. So the current is the same, the charge is I times t, the charge is I times t, the current is the same, and of course even the time is the same. That means the charge is going to be just Q. The current is the same because these parts are in series with each other, but it is for the same time. Therefore, the same charge is passing through point S. The same charge will pass through point S as that passing through point, because they said charge Q passes R in time t. So the charge passing R is the same as the charge passing S, because charge is equal to I times t, the current is the same and the time is the same, so the charge is the same. The answer is going to be B. 4 wires are made of the same metal. That means the resistivity is the same. So resistance is equal to rho L over cross-sectional area. The cross-sectional areas, lengths, and thermodynamic temperatures of the wires are shown. Which wire has the largest resistance? So resistance is directly proportional to length. Okay, and inversely proportional to cross-sectional area for the same wire. So this is constant. So the one with the greater length and the smaller cross-sectional area should be having the highest resistance. So we have, and by the way, resistance is also directly proportional to temperature. So it should also be having a higher temperature. So those ones with the one with the highest length, we have this one and this one. Then we check their cross-section area. One with the smallest cross-section area, so we have taken this one, we ignore this one. Then we check the temperature. The temperature is the same. So the answer is going to be A. Resistance is directly proportional to temperature. Resistance is directly proportional to air. Resistance is inversely proportional to cross-section area. So temperature should be greater, length should be greater, cross-section area should be less. A cell with internal resistance is connected to a variable resistor R as shown here. The resistance of R is gradually decreased. How do the current I and the terminal PD across the cell change? So we have already seen that e.m.f is equal to terminal PD plus the lost volts. So terminal PD is equal to the e.m.f minus the lost volts, but remember the lost volts is current times the internal resistance. The resistance R is gradually decreased. So if R is decreased, it means the current I increases. If I increases, it means the lost volts increase. So lost volts increase. So this part is becoming bigger. If the lost volts increased, it means the terminal PD actually decreases. So the terminal PD must decrease because the current increases, so ignore those ones. The lost volts must decrease. So the terminal PD decreases, so our answer is going to be C. Kirchhoff's first law states that the sum of currents entering a junction in a circuit is equal to the sum of currents leaving the junction. That one is conservation of charge without wasting any time. That is A. It is a consequence of conservation of charge. The second law is a consequence of conservation of energy. A circuit contains two batteries, each of negligible internal resistance, and two resistors as shown here. The galvanometer has a current reading of 0. If the galvanometer reads 0, the PD across this part here should be the same as the PD across the other one, which is the same as e.m.f of the cell. What is the e.m.f of the cell? So that is very easy. I just look for the PD across 3 ohms. Using the potential divider formula, that is V out is equal to that resistance over total resistance times the voltage input. So this is going to be 3 divided by 3 plus 9, which is 12 times 24. That gives us, I think, 6 volts. So our answer is going to be A. Which two units are used to define the volt? Remember we said that PD is equal to the energy transferred from, say, electrical to thermal per unit charge. So it is energy or work done per unit charge. And this is joules, and this is coulombs. So the units that can define a volt, which is the unit of PD, is most like a joules per coulomb, joules and the coulomb. So we have a coulomb and joule, so the answer is B. The graph shows the variation with the length of the resistance of a uniform metal wire. The gradient of the graph is G. The wire has cross-sectional area A. Which expression could be used to calculate the resistivity of the metal wire? So we know that resistance is equal to rho times L over cross-sectional area. It is a graph of R against L, so it means the gradient G is equal to rho divided by A, which means resistivity is going to be the gradient times A. So our answer is going to be option A. Diagram 1 shows a lamp connected to a supply through two switches. During repairs, an electrician mistakenly reverses the connections X1 and Z1 so that Z1 is connected to supply X1. To the other switch so that Z1 is connected to the supply and X1 to the other switch at Z2. X1 is to X1 to the other switch at Z2, okay? As shown in diagram 2. So which switch positions will now light the lamp? So the switches that we have here are Z1 and Z2. So let's check, let's do some what we call inspection. Which switch positions will now light the lamp? Suppose X1 is put to Y1. So X1 is put to Y1. X1 is taken to Y1, okay? So we bring X1 here. It means we are opening the power supply. There will be no energy supply, so this is automatically wrong. X1 to Y1, X1 to Y1, it is still the same thing. This part will be open. It means this will not work. Then X1 to Z1, that part is closed. And X2 to Y2. If we close here and X2 is to Y2, it means this part is open, the circuit is incomplete. If we close, we say X1 is connected to Z1 like this, and X2 is connected to Y2. It means the circuit is incomplete. This will not light. Let's say X1 is to Z1, and X2 is brought to Z2 here. The circuit is complete, so it means this one will work. So our answer is going to be D. A wire supplying a shower heater with a current of 35 amperes has a resistance of 25 milliamperes. What is the power dissipated in the wire? So without wasting time, power is equal to I squared times R. So the current is 35 squared times the resistance, which is 25 times 10 power negative 3 ohms. So let's check from our calculator. 35 squared times 25 exponent negative 3. So that is going to give us 30.6, or approximately that is giving us 31 watts. So this is approximately 31 watts, which is A. The student has a set of identical cells and identical lamps. The cells have negligible internal resistance. A lamp connected to a cell lights with normal brightness. So this one is normal brightness. What happens when the student connects the lamps and the cells as shown? So what happens there? So here we can use, maybe we can use Kirchhoff's laws. Let's say they have the same resistance, assuming they're identical. If I use Kirchhoff's laws here, let's say the e.m.f of this is E. So the PD here, the PD across R was the same as e.m.f. So if I use Kirchhoff's laws here, so here I have the e.m.f, the sum of the e.m.f's is E, sum of PDs will be the current here, so it will be current, let me call it I1 times R plus the current I2 times R. Let's say the current here is I2. It means the PD across 1 has reduced. The PD across 1 is smaller, and the PD across 2 is smaller than actually E. Let's check if we put a loop there, which is also clockwise. Let's consider such a loop. It means the sum of EMFs is going to be twice E. The sum of PDs will be the PD across this one, that is PD across 1 plus the PD across 3. So it means the PD across both of these, the sum of the PD across 1 and 3 is twice the PD across is twice the EMF. Okay, so let's see what happens when the student connects the lamps and the cells as shown. Number 1, all 3 lamps light with the normal brightness. That is not possible because we have seen that the PD across them is less than the EMF. We have seen the PD across 1 is when they are like this, and the PD across 2 is less than the EMF. Only lamp 2 lights with normal brightness. Only lamp 2 lights with normal brightness. That will not also be true because the PD across it is already less than E. Only lamps 1 and 3 will light with normal brightness. That is going to be very true because when you use an external loop, when I considered an external loop here, ignoring the one at the center there, it means that twice EMF, because this is E and that is E, twice EMF would give us the PD across 1 and the PD across 2. Since this is twice, and yet the PD across 1 was across one of these was E, it means the EMF is twice. Therefore, it means the PD across each of these could be actually equal to the EMF. Therefore, this is going to be C. A potential divider circuit is shown. What is the resistance of resistor R in the potential divider circuit? That is very simple. Oh, by the way, I can take you back here and I use Kirchhoff's laws fully. So here I can say for the first one, for the first loop, E equals to the PD across 1, E is equal to V1 plus V2. So I will have another equation that E is equal to V1 plus V2. And for this one, if I combine these two, remember twice E is equal to V1 plus V, twice E is equal to V1 plus V2. So I will say twice E, where there is E, I'm putting V1 plus V2 is equal to V1 plus V3, which means no, let me just use this loop here and this one. Let me ignore the one at the center, but of course the answer is going to be C, I'm very sure. I just want to use Kirchhoff's law so that people can see. So let me ignore substitute the first loop, let me ignore the outer loop, and I just look at this one here. What's wrong with my eraser? Okay, if I decide to consider those two loops, you are going to notice if the loops are anticlockwise, the first loop E is going to be equal to V1 plus V2. If I consider the second loop, E is going to be equal to V3 plus V2. And if you combine these two, you are going to notice that actually V1 plus V2 is equal to V3 plus V2. So it means V1 plus V2 is equal to V3 plus V2. So which means that V1 is equal to V3. So the PD across 1 is the same as the PD across 3. So if we go back, if the PD across 1 is the same as the PD across 3, then it means if I go back to the outer loop here, which was giving us twice E being equal to the PD across this one, which is V1, plus the PD across the other one, which is V3, ignoring the one at the center. Remember, V1 is equal to V3, so it means twice E is equal to V1, for example, plus V3, which is the same as V1. So I'll put here V1. So it means the PD across V1 is going to be equal to E. The PD across 1 is E, and which also means that the PD across 3 is also E. And E is the full EMF, so the lamps will have full brightness. V1 is equal to 3, meaning that V3 is also equal to E. So these have full EMF. The EMF is the same as the PD across them. They have full brightness. Okay. Okay, so here, what is the resistance R of the resistor R in the potential divider? So this is a potential divider. So resistance, we know that V out is equal to that resistance over total resistance times the voltage supply or voltage input. V out is 5 equals to R over total is 150 plus R, then times voltage input, which is 12. So I'll just press my calculator here, collecting like terms, 5 divided by 12, which is, okay, let me leave it as 5 over, I just cross multiply 5 into 150 plus R is equal to 12R. Open brackets, 5 times 150. So we have 750 plus 5R is equal to 12R. Subtract 12 minus 5, that is, I think, 7. So 7R is equal to 750. And what is R? R is 750 divided by 7, which is 107. So So the answer will be B. 2 cells of e.m.f. 3 volts and 1.5 volts and negligible internal resistance are connected to resistors of resistance 9 ohms and 18 ohms as shown here. What is the current I in the 9 ohm resistor? So first of all, we can find the PD, or we can find total EMF anyway. This is 3 volts and that is 1.2 volts. They are connected the other way around. That means the total EMF is going to be 3 minus 1.2, which is going to be 1.8 volts. So note that that PD, that EMF is the PD across each of these. So to find the current, we shall get the PD, which is the EMF over the resistance, which will be 1.8 divided by 9. But I think this is 0.2. So our answer is going to be B. Because these ones are connected the other way around, this is 3 volts the other side, the other one is 1.2 the other side. That's why I subtracted if I consider the loop here. A metal plate of uniform thickness is connected to a cell as shown here. Electrons move clockwise around the circuit. So electrons are moving like this around the circuit. Which statement about the metal plate is correct? Okay, remember current is equal to never. That means the drift speed is going to be the current divided by NE times the cross-sectional area. Electrons are moving from right to left because they are moving clockwise. Notice that as they move in this direction, the cross-sectional area is decreasing. And when the cross-sectional area decreases, it means the drift velocity must increase. The current is constant because the all parts are, it's like it's just a single conduct, so the current is constant. N and E are constant, so but the cross-sectional area is decreasing, meaning the drift velocity must be increasing. So which statement is correct? The average drift speed decreases, it actually increases. The average drift speed increases as they move from right to left. I think this is true. The average drift speed of electrons increases as they move from right to left. Yes, because the area decreases, so the average drift speed increases. The block shows the direction of the current in a metal. The diagram shows the direction of the current in a metal block. The charge carriers enter the block through the face PQRS, which means the cross-sectional area is going to be this area here. So the cross-sectional area is going to be, this is X, that is X times Y, that is the cross-sectional area. The number density of charge carriers N, each charge carrier has charge E, the average drift speed of the charge carrier is V. Which expression gives the current in the block? So we know that current should be equal to never. Current should be equal to never. So N is given, E is given, the V is given, it is on the area. So the current is going to be equal to NEV, where there is area, I'll put X times Y. So this is X times Y, that is the area. So our answer is going to be precisely B. What could not be used as a unit of potential difference? Let's see. This is ampere, ohms. Ampere is current, ohms is resistance. So that can be V is equal to IR. That is correct. Let's check this one. This is newtons per meter per coulomb. This is not really very correct, because the unit which has newtons per meter per coulomb could be V is equal to work done over charge. Work done is force times distance, which is Newton meters, over charge, which is coulomb. So the most appropriate would be Newton meters per coulomb, not newtons per meter. Let's first check this. Watts per meter. Watts is power per ampere, and ampere is current. That is correct because we know formula V is equal to, power is equal to I times V, meaning V is power over I. So this one is correct. Let's check this one. Ohm watts power a half. We have an equation of power as V squared over R, which means V can be the square root of power times R, where power is watts and R is ohms. When I find the square root, this is correct. So most likely this is the one which is not correct, because it's supposed to be Newton meters per coulomb, not newtons per meter per coulomb. Which graph shows the resistance R of a filament lamp? How the resistance of a filament lamp varies with the applied potential difference as V increases. Okay. So, of course, C is automatically wrong because it shows that the resistance remains constant. The resistance increases as temperature increases. The resistance must increase as temperature increases. Then B is also wrong because it shows that the resistance increases, and actually it is even wrong because it shows that when there's no PD, the filament lamp has no resistance. That is not possible. For every wire, it has some resistance, so the graph cannot start from zero. Then A could be correct and D could be correct. But what happens to the resistance as the PD increases? Of course, as the PD increases with the time temperature increases, the resistance must increase. That means D is wrong and A is going to be correct. So our answer is A. Kirchhoff's two laws for electric circuits can be derived by using conservation laws. On which conservation laws do Kirchhoff's laws depend? Of course, first law is charge, second law is energy. So we are aware about that. We don't waste time there. Charge and energy. Charge for first law, conservation of charge. Sum of currents into a junction equals sum of currents out of a junction. That is charge, because current is the rate of flow of charge. Then the second law, sum of EMFs is equal to the sum of PDs. EMF and P, that is energy. So the answer is B. The diagram shows a circuit. Which statement about the circuit is not correct? Okay. A, the EMF or electromotive force is the energy transferred per unit charge. So EMF is the energy transferred per unit charge. I think that is correct, although it is chemical to electrical. Energy is transferred from chemical potential energy in the cell to other forms when the switch is closed. That is also true. The electromotive force of the cell is greater than the terminal PD. That is always true. The EMF is always greater than the terminal PD. When the switch is open, the voltmeter measures the EMF of the cell. When the switch is open, the voltmeter actually will give no reading because there is no current flowing in the circuit, so there is no PD across the battery, so this is not correct. However, if the switch was closed, the voltmeter could give the PD between the terminals of the cell. It will not give the EMF. But if the voltmeter had been connected across here and the switch is open, then it would be giving the EMF. The diagram shows a circuit containing 4 voltmeters. The readings on the voltmeters are V1, V2, V3, and V4. All the readings are positive. Which equation relating the voltmeter readings is correct? V1 equals to V2 plus V4. Automatically, that is wrong because V1 is the same as V2 because these are actually in parallel. So V1 is supposed to be the same as V2. So it means this is wrong. V1 equals to V2 plus, that is automatically wrong. V1 should be the same as V2. V2 plus V3 is equal to V4. That is not true. V2, which is the same as V1, is going to be the same as V3 plus V4. So If V1 is not brought again here, I will ignore it here and I concentrate on V2 equals to that. So the only option we have here is V3 plus V4 equals to V2, or V3 plus V4 minus V2 equals to 0 when I bring this one the other side. This and I take it the other side, so the answer is going to be D. This one is wrong because it would mean that V4 minus V3 is equal to V2, which is not correct. So the total PD across here is the same as the PD across this, which is the same as the reading of V2, which is the same as the total PD across the other combination there, which is V3 plus V4. A network consists of 3 ohm resistor and two 6 ohm resistors as shown. The potential difference across the network is 4 volts. What is the current through the 3 ohm resistor? Note that this 3 is a half of this. If the current here is I, the current here is going to be twice I, because remember, current is inversely proportional to resistance. This resistance is twice the other one, so the current here is a half the current there. Let's find total current. Total current is going to be equal to the e.m.f divided by total resistance. So the e.m.f is 4, total resistance is going to be, of course, these are in parallel, so we have here 6 times 3 divided by 6 plus 3, then plus the one in series, which is 6. So that is 18 over 9, which is 2. I'm finding total resistance, remember. So that is 2 plus 6, which is 8. So this is going to be 8 ohms. Total current is 8 ohms, 4 over 8 ohms, which is 0.2 amperes. So that is the total current. And then what is, no, it is not 0. It is 0.5. Half is 0.5. Okay, so the total current is 0.5. So remember the current, if the current through 6 is I, the other one is twice I. So I'll say I, no, let me say I1. Okay, this is I total. So I plus twice I should give us 0.5. So it means I is going to be 0.5 divided by 3 because it's 3I. So 0.5 divided by 3, that is 0.17. So that is 0.17 amperes. So what is the current through the 3 ohm resistor? So the current through the 6 is 0.17. So the current through the 3 ohm is going to be twice. So the other one is twice, so times 2, which is 1.3, 0.33 recurring. So twice I is going to be 0.33 recurring. So the answer is going to be C. In the circuit shown, all the resistors are identical and all the ammeters have negligible resistance. The reading A1 is 0.6 amperes. So here it is 0.6. The current here is 0.6 amperes. What are the readings on the other ammeters? Okay, so I'll use Kirchhoff's laws. I'll put the first loop here. Let it be clockwise. Let this e.m.f be E. So the question is, what are the readings on the other ammeters? So for this loop, the e.m.f is E is equal to PDs. We have let the PD the resistance here be, this is R plus R, that is 2R. So we have 2R times 0.6, assuming the current is the same direction as the loop. So that is the one equation. Then we can look at the second equation here. I'll also put this in the same direction. So the e.m.f is E, and the current here, when it reaches here, it is going to divide. It is going to take that route. And let's say the current here is going to be I2. Let me call this current I2. I'll just call that current I2 and I'll call this one I3. Maybe this is I1, but this is not necessary because there's no potential difference. There's no resistor there. So E is going to be, because this is the other way around, I've put this to be the other way around and I'm moving in that direction. So E will be positive. If I move clockwise, E is going to be positive, but this will be negative I2 times the resistance R. So when we combine these two, I can find I2. Of course, the negative will just show an opposite direction. So I'll have that negative I2 R is equal to 1.2 times R. I've combined these two equations. So it means I2 is equal to negative 1.2 amperes, or simply in magnitude it is 1.2. So I check for 1.2. 1.2 for A what? A3. 1.2 for A3, it is here. So I don't even need to check the rest. The answer is going to be D. Because these are all wrong. So 1.2 is in D. So the answer is automatically D. Even if I don't use the third loop here, but you can use all the loops and check. When the current in a wire is 5 amperes, the average drift speed of the conduction electrons in the wire is 7.4 times 10 power negative 4 meters per second, which law gives a possible cross-sectional area and number of conduction electrons per unit volume for the wire. Okay. So we know that current is equal to never. Current is equal to never, so I will make I over V times E the subject. This is going to be N times A. So let me first find I over V times E because they have given us the drift speed. So this is going to be a constant. IVE is going to be a constant because the question is which row gives a possible cross-section area and number of conduction electrons per unit volume for this wire. I over V is going to be a constant. So the product N times E should give us that constant. Let's first find that constant. I is 5. Then V is 7.4 times 10 power negative 4. And then E is 1.6 times 10 power negative 19. So let's first find that constant. 5 divided by 7.4 exponent negative 4 1.6 exponent negative 19. So this is 4.2 times 10 power 22. So the product should give us 4.2 times 10 power 22. So we have to check which of these products give us that, because this is A and this is N. So we are just going to check. I can even just check the numbers in the front. 7.2 times 1.2. That is not 7.2 times 5.9. That is not going to be. We have 2.3 times 7.3. That is not true. 2.3 times 3.7. Did I compute this wrongly? Let me check it again. 7.2 times 1.2. Okay. 7.2 times 5.9. Okay, so the answer is going to be B. So the answer is going to be B. You can check carefully. 7.2 exponent negative 7 times 5.9 exponent 28. So it is 4.2 times 10 power 22. So the answer is going to be B. A fixed resistor of resistance 12 ohms is connected to a battery. There is a current of 0.2 amperes in the resistor. The current is now doubled. What is the new power dissipated? So the current is now doubled. What is the new power dissipated? Okay, so because the current is doubled, the new current is 0.4 amperes. Without wasting time, power is equal to I squared times R. So the current is now going to be 0.4 squared times R, which is 12. So this is going to be 0.4 squared times 12, which gives us 1.9 watts. So our answer is going to be C. There is a current in a resistor for an unknown time. Which two quantities can be used to calculate the energy dissipated by the resistor? Which two quantities can be used to calculate the energy dissipated by the resistor? Of course, we know that PD is equal to the energy dissipated per unit charge. So the energy dissipated is going to be the PD times the charge, number one. The current in the resistor and the potential difference across the resistor. So I times V will give us the power. That will not give us the energy dissipated, so this is not correct. B. The resistance of the resistor and the current. I times V will give us only the PD, so this is not correct. The total charge passing through the resistor and the potential difference. V times Q will give us the energy, so this is correct. So the answer is going to be C. Two cells with e.m.f. E1 and E2 and internal resistance R1 and R2 are connected to a resistor as shown in the figure here. Okay. The terminal PD across cell 1 is 0. The terminal PD across cell 1 is 0. Which expression gives the resistance of resistor R? Okay. So if the terminal PD across cell 1 is 0, we know that e.m.f. is equal to the terminal PD plus the lost volts. So it means the terminal PD across cell 1, I'll call it V1, is equal to, they have said it is 0, and is equal to the e.m.f, which is E1 minus the lost volts. But remember, the lost volts in cell 1 will be the current. Of course, the current is the same. The lost volts here is going to be I times R1. So this is going to be current, which is I minus small r1. That is the lost volts there. Which means the current I is going to be, I will now just take the other part of the equation. So the current I is going to be E1 divided by small r1. Okay. So then, which expression gives the resistance of resistor R? So now I'm going to draw in a loop. I'm going to draw in a loop. So I will draw in a loop which is anti-clockwise. So if I consider that loop, if I consider that loop, sum of EMFs will be E1 plus E2, that is the sum of EMFs. Sum of PDs will be the current I into the total resistances, which will be R plus R1 plus R2. But note that I is E1 over R1, so it means E1 plus E2 will be equal to E1 over R1 into R plus R1 plus R2. Okay, so I'll just cross multiply. So when I cross multiply, I'm having E1 R1 plus E2 R1. I'm also opening the bracket, so I have E1 R plus E1 small r1 plus E1 small r2. So E1 R1 has cancelled out. So we want to make capital R the subject, so I'll have I will have that E2 R1 minus E1 R2. Then I divide this by E1. This will give me R. So it means my answer here is going to be obviously A. My answer there is A. E1, E2 R1, E1 R2 over E1. A battery has an EMF of an EMF E and internal resistance R. The battery delivers a current I to a variable resistor and the potential difference across its terminals is V. The variable resistor is adjusted so that I increases. Why does V decrease? So remember, we have already seen that EMF E is equal to the terminal PD plus the lost volts. So meaning the terminal PD, which has been labeled V, is equal to the EMF, which is of course constant, minus the lost volts, which is current, times internal resistance. So if I increases and E is constant, means V must decrease. So if the lost volts increases, the variable resistance is adjusted so that I increases. Why does V decrease? So A, the EMF decreases? No, that is not true. The EMF is constant. The internal resistance R increases. It may not be increasing, it may be constant. The PD across R increases, that is the lost volts increases, so the answer is going to be C. Three identical resistors are connected between terminals P and Q in different networks X, Y, and Z as shown. What is the order of increasing combined resistance? Okay, so you can find the total resistance here. You can find total resistance here. Should I use a simple resistor? But because they are identical, let's say this is R plus R, then this is, okay, I'm just going to use values. Let me use 10. Let me use 10 ohms. 10, 10, 10. So here we have 20 and we have 10 here. So 20 times 10 over 20 plus 10. This gives us 200 over 30, which is 20 over 3. So this is 20 over 3. So I'm using 10, remember? Because these are in parallel, I will get 1 over 10 plus 1 over 10 plus 1 over 10. Then I get the reciprocal. So it will be 10 over 3. Because it's 1 over 10 3 times, then I get the reciprocal to be 10 over 3. Then here, remember, it is 10, 10, 10. So these ones are in parallel. So this gives us 5. 5 plus 10, this gives us 15 ohms. So this is the highest. In order of increasing, the highest should be Z. So Z should be the last. Then the smallest is, I think the smallest is 10 over 3. So the smallest is Y. So the answer is going to be C. So you could also have chosen resistors of different magnitudes, or you could use R. In general, if you are very good at algebra, you can use R. The diagram shows a variable resistor R and two fixed resistors connected in series in a circuit to act as a potential divider. The cell of The cell of EMF 6 volts has negligible internal resistance, a cell of EMF 2 volts, and a galvanometer are connected into the potential divider. So this is what we have. The resistance of R is varied until the galvanometer reads 0. That is very beautiful. When the galvanometer reads 0, if this gives 0, it means the PD across these 2 points is the same as 2 volts. So it means the PD across the fixed resistor plus the PD across 2 ohms should give us 2 volts. So this means if the PD across this is 2 volts, it means the PD across, I will call it V across 10 ohms is going to be therefore 6 minus 2, which is going to give us 4 volts. So this is going to be equal to 4 volts. Something is wrong with my pen. I think the battery has worn out. Okay, so if the PD across these two is actually is 2 volts, then the PD across the other one must be 4 volts. Okay. So what is the resistance of resistor R? The 4 volts that we have obtained can help us to find the current. Those 4 volts can help us to find total current. So we have the total current I. Total current I is going to be equal to 4 divided by 10. What's wrong with this pen? 4 divided by 10, which is going to give us 0.4 amperes. Sorry about my pen. My pen is now stressing. Okay, so let's now find it. We want to find what is the resistance of resistor R. That's what we want to find. So we can now find the PD. Since we know the current which is flowing, we can find the PD across. We can find the PD across 2 ohms. Since the PD across 2 and R is 2 volts, we can find the PD across 2 ohms. How? So the PD, remember, across the 2 ohms is going to be equal to the PD across the 2 ohms is going to be the current, which is 0.4 times the 2. So it is 0.4 times the 2, which is giving us 0.8, which will be 0.8 volts. So that is the PD across the 2 ohms. But remember, the total PD across R and 2 ohms is 2 volts. That means the PD across R is going to be equal to PD across R is going to be 2 minus 0.8, which is 1.2 volts. That is the PD across R. Since the current is 0.4, because the current is the same, then we shall find the resistance from the PD over the current. So the resistance is going to be equal to the PD, which is 1.2, divided by the current, which current is divided by the current, because it's V over R or V over I, the current is 0.4. So we can press our calculator. 1.2 divided by 0.4, that gives us 3. So R is going to be equal to 3 ohms. So our answer is going to be A. Okay, let's part 3 stop there because my pen is having issues. Let me work on the pen. We shall meet in part 4. All the best. I hope you learned something from this. See you in part 4.